Welcome to the recycle reactor and autocatalytic reaction system under the head of polymer reaction engineering. Now, before we go into detail, let's have a look at what we studied previously. Previously, we discussed about the preference for various kind of a reactor which are being in practice. Then we had a discussion about the plug flow reactor in series and a parallel. Then we discussed about the mixed flow reactor in series. We had a discussion about the different type of reactors in series, and we had a discussion about the best arrangement to be suited for any kind of ideal reactor system. Now, in this particular lecture, we are going to discuss about the recycle reactor and autocatalytic reaction system. Now, recycle reactors, they are very common in the chemical engineering as well as the polymer reaction engineering, polymer engineering aspect. And this type of chemical reactor, product stream is usually split in and returned to the entrance of the reactor to enhance the conversion of the reactor. Now, see, sometimes because of the requirement of space, because of the requirement of other limitations to cater the need of other limitations, we may have the reactors which is not as per the required size. So, in that case there are certain reactant streams, those who enter into a particular reactor may unreacted. So, at the outlet at this point you may separate all those things and then you may send back all those things to the inlet of the reactor for the better conversion, and rest remaining thing you may have as an output. So, other things are always same, like feed rate, concentration, molar conversion, etc. All these things are remaining same, and we have designated all these things in their respective notations over here. Now, if you see that at point 1 we are feeding the fresh feed, and the recycled streams usually they are mixed, and the combined input feed is to the reactor at point 1. Now, here you may have to look into couple of points. One point is that when we talk about the things related to the concentration, when we talk about the things related to the feed rate, then we have to look into this aspect that the return stream or recycling stream is also participating into the input stream. So, this particular approach we need to be to address while considering all these things. So, sometimes we need to look into that what should be the my recycle ratio, and how we can utilize this recycle ratio in respective time. So, recycle ratio is referred as a volume entering the entrance of the reactor divided by the volume leaving the reactor system. So, keeping in view of this particular figure in cognizance, the recycle ratio is referred as FAR upon FAF. FAF is the output feed rate and FAR is the recycle rate. Now, when we talk about the composition of the fluid in the stream, usually which is situated at this location number 2, then R and 3 are the same, then for the conversion of the reactant in the various terms can be given, and they attract more important aspect comparatively the recycle reactor system. And sometimes you may need to address the things related to the single pass conversion and overall conversion system. Now, let us have a look about this particular thing, that when we talk about the single pass conversion. Now, single pass conversion FA1 this is my equation number 1. Now, where we can say that FA1 that is equal to the molar flow rate of reactant A at point 1, and FA2 is the molar flow rate of reactant A at point 2. So, we can write the overall conversion x naught, or we can say XAF is equal to XA3. So, we can write more general equation that x naught is equal to FA naught minus FA3 upon FA naught. This can be represented as equation number 2. Now, sometimes people may look into the steady state conversion during the concept of recycle reactor. So, at a steady state condition, the location 1, that is the inlet of the reactor, there is a mixing of a fresh feed and converted stream. So, these two streams are being mixed. Therefore, the determination of the conversion at point 1 after say time t, that XA1, the relationship between the single pass conversion and overall conversion is more important. Now, to find out the conversion at point 1 and the relationship between the overall and per pass conversion, there is a requirement of several relationship of flow rate and conversion from the recycle reactor, which we can develop like this. When we try to develop, that is the relation of flow rate and conversions at different point. So, we can write x naught is equal to FA naught minus FA3 upon FA naught, that you can represent like equation number 1. It is different with the previous one. Now, XS is equal to FA1 minus FA2 upon FA1 2, and then we talk about this recycle ratio FAR upon FA3, that is represented as equation number 3. Now, if we try to write the mole balance at point 1, then we can write the mole balance equation with the respect to this flow rate FA naught plus FAR, that may be equation number 4. So, mole balance at point 2, that is this point 2, that can be written as FA2 FAR plus FA3. So, that we can say that this is my equation number 5. So, in this case we need to find the relationship in between FA naught, X naught, XS and R after eliminating FAR, F1, FA1, FA2 and FA3. So, how we can eliminate these things from these 5 equations? So, if we try to write the eliminating FAR, this can be given as FAR is equal to Rx FA3. That is from equation, if we talk about the equation 4, then FA1 is equal to FA naught plus RFA3, and if we take the help of equation 5, then FA2 R plus 1 FA3. So, X naught will become FA naught minus FA3 upon FA naught. Similarly, XS, this become FA1 minus R plus 1 FA3 upon FA1. This is again. Now, if in the second step, if we try to eliminate FA3, so FA3 can be given as FA naught 1 minus X naught, or FA1 is equal to FA naught 1 plus R 1 minus X naught, and FA2 is equal to R plus 1 FA naught 1 minus X naught. and this is Fa1 minus R plus 1 Fa naught 1 minus x naught Fa naught. So, this is again the important equation. Now, if we eliminate Fa2 and Fa1, so excess is equal to Fa naught 1 plus R into 1 minus x naught minus R plus 1 minus x naught Fa naught divided by Fa naught 1 plus R into 1 minus x naught, or after rearrangement it can be given as 1 plus R plus 1 plus R minus R x naught from this equation minus R minus R x naught plus 1 minus x naught. This is divided by 1 plus R 1 minus x naught. So, at last we can write excess is equal to x naught upon 1 plus R 1 minus x naught, and if we rearrange this, then it can become x naught is equal to 1 plus R xs upon 1 plus R xs. Now, this is the required relationship between the overall conversion and single pass conversion. Now, so after mole balance at point 1, the conversion at this point can be calculated with this particular approach. Again, we need to draw this reactor just for the ease of understanding. So, this is point 1, 2 and 3. So, Fa1 that is mole balance at point 1. So, Fa1 Fa naught plus Far, it is the mixed stream, because here this is the mixed stream. So, if there were no reaction, the concentration of A would be higher because of the reason quite obvious. So, Fa3 is equal to Fa naught, let us say, then Xa1 is equal to Fa naught plus R Fa naught minus Fa naught plus Far upon Fa naught plus R Fa naught. Now, here we can write Xa1 is equal to R. If we try to rearrange the things, R Fa naught minus Far upon Fa naught 1 plus R. So, and Far is equal to R Fa3 and Far is equal to R Fa naught 1 minus x naught, or x1 A1 is equal to R x naught upon 1 plus R. So, this is the required equation, which is sometimes very useful for assessing the things. Now, we can use the recycling in the plug flow reactor, because sometimes it is quite useful in the industrial approach. Therefore, to write the differential form of performance equation for plug flow reactor and putting the initial value of molar flow rate at the entrance of the reactor, R plus 1 Fa naught with the conversion Xa1, it can be given as such. So, the performance equation for PFR with the recycling can be V upon Fa1 Xa1 to sometimes referred as XAF, X naught, etc., dXA minus RA. Now, where FA1, that is equal to the feed rate of A entering in fresh feed plus A entering in entrance which is unconverted and coming from the recycle stream. So, mathematically if we try to write this thing, that is, that will become FA naught plus FA naught R, or FA1 will become FA naught 1 plus R, that is the recycle ratio. Now, V can be represented as V is equal to FA naught 1 plus R XA1, XA2, XAF is not dXA upon minus RA. Now, this form of equation in terms of conversion, this can be used for any epsilon, that is for the varying volume system. So, if we say that XA1 is equal to R x naught upon R plus 1, then V is equal to FA naught 1 plus R x naught upon R plus 1 x naught dx A upon minus RA. Now, for a special case when epsilon A is equal to 0, or for constant density system, it can be represented with respect to the concentration term. So, tau may become Ca naught V upon Fa naught, this is equal to minus R plus 1 Ca naught plus R Caf upon R plus 1 Caf dCa upon minus Ra. That is for the epsilon A is equal to 0. So, this is you can say. Now, suppose sometimes people may opt for graphical representation. Now, before we go into the graphical representation, here you see that there are various type of epsilon. This is the general representation, and it is for the special case when which we discussed, that is epsilon is equal to 0. In that case, you can see that this one is the recycle ratio here, and these extremes of the plug flow reactor sometimes approaching to R tends to 0, and the mixed flow reactor approaching to R tends to infinity. Now, sometimes when we see that the recycling ratio is negligible for PFR, so on putting the values of R, that is the recycle ratio, that R is equal to 0 in the performance equation which we discussed, the recycling reactor approach to PFR and the performance equation is formed same as the performance equation for the PFR. Now, we can write these equations in the following form. Let us take the example that when the recycling is negligible, that is R, sometimes you may take that R is equal to 0, and the performance equation for recycle reactor, that is V upon Fa naught R plus 1 R x naught upon R plus 1 x naught dxa upon minus Ra. Now, if we put R is equal to 0 in this equation, then it may become V upon Fa naught is equal to 0. Now, this is the performance equation for PFR. Now, if we talk about the recycling ratio is infinite. So, in putting the value of R tends to infinity, sometimes we use this equation, this particular condition in mixed flow reactor. So, mixing of fresh feeding system sometimes may take place. So, in that case, the performance equation for recycling reactor approach to mixed flow reactor, the required performance equation can be modified like this when R is equal to infinite. So, putting the value of R in performance equation in the for the recycled reactor, we have 1 upon F A naught, sorry, V upon F A naught is equal to x naught upon minus R A. So, this is my final equation. This is the performance equation for mixed flow reactor system. Now, this you can draw, we can draw with various plots, and you can see that for small reactors and large reactor there is a wide variation in the particular approach. Now, let us have a look about the autocatalytic reaction. Now, before we go for the performance equation of these autocatalytic reaction system, let us have a look about what are these reaction systems. So, in this type of a reaction, one of the product act as a catalyst, that is quite obvious, and it is a CO motto from the catalytic autocatalytic concept. Now, such type of reaction start with some of the product present in the little amount, and then they can approach and then they can start the things exponentially. Now, generally when we talk in terms of a mathematical approach, the simple type of reaction of nth order, that is n is greater than 0, that means the positive order reaction, that is carried out in the batch reactors. The rate of disappearance is usually high at the start of the reaction and then decrease with the consumption of the reactant, that is quite obvious. In autocatalytic type of a reaction, the rate at the start of the reaction is very low due to the presence of the product in the trace amount, and then increases because the product acts like the catalyst. So, then they they have the tendency to increase to the maximum value, where the concentration of the reactant and the products, they sometimes become equal. So, when we say that the mathematical approach, so this can be represented as the autocatalytic reaction, they can be represented at A plus R is equal to R, and the rate equation for autocatalytic reaction minus RA KCA CR. So, the total moles of A and R remaining constant at any time. C naught is equal to Ca plus Cr, or Ca naught is plus Cr naught, that become the constant. Now, the rate equation, you can write the rate equation, that is quite easy. Ra is equal to minus dCa upon dt K Ca C naught minus Ca. So, this is the start of this autocatalytic reaction. Now, if we try to rearrange this equation, then it becomes minus dCa upon Ca upon C naught K dt. So, if we break into the partial fractions, in that case it becomes minus 1 upon C naught dCa upon Ca plus dCa upon C naught minus Ca K dt. Now, if we integrate the things, then we may have ln Ca naught C naught minus Ca upon Ca C naught minus Ca naught is equal to C naught Kt, and Ca naught plus C Kt. Now, if we try to represent these things into the graphical representation, it is quite simple. Now, see here you are having this things at the start. Now, this is Ca. Now, here you see that at the start we are, when you are having negligible product, and as long as if it goes on increasing, then the product which is being formed during the course of the reaction, it acts like a catalyst to the reaction mass, then this may go up to the maxima. Now, when it approaches to this particular maxima, at that particular point of time it may go down. The reason is that because the reactant maximum amount of reactants in the reaction mass may get consumed over the period of time. So, this is the progress of time. And if we talk about sometimes you may talk about the start with some R present. In that case you may have this type of a curve, and if there is no R in the feed, then you may have like this. So, you can calculate the C, in that case Ca is equal to Cr and Ca naught Ca upon Ca naught. So, when we conceptualize this thing, here in an autocatalytic reaction, a batch reactor, there some R must be present. Starting with a very small concentration of R at this start, we can see that the rate will rise as R is formed. Now, at the outer stream, when A is just about to used up, so the rate must drop at to the 0. Now, this also shows that the rate follows a parabolic approach, and the maxima where the concentration of A and R both are equal. So, you can see that here the maxima, the concentration of both are equal. Now, usually when we try to write the mathematical approach for the optimization purpose of these autocatalytic reaction, in that case we can write these equations like minus Ra is equal to Kca C naught minus Ca. On differentiating these equation with respect to dCa on both sides, then we can have d minus Ra upon dCa, that is equal to d k Ca into C naught minus Ca upon dCa. Now, for maxima, if we consider for maxima, this equation, from this equation we can write that d minus Ra upon dCa will be equal to 0, or sometime it implies that k into 1 C naught minus Ca plus Ca 0 minus 1, that should be equal to 0, or k C naught minus Ca plus 0 minus Ca is equal to 0, or k C naught minus 2 Ca is equal to 0, or k is equal k Ca plus Cr minus 2 Ca is equal to 0, or k is k Cr minus Ca is equal to 0, or in that case Ca is equal to Cr, that is at maxima, that which we have discussed, we have already discussed in the previous one. Now, when we talk about the comparative note of flow versus mixed flow reactor used for the autocatalytic reaction, the comparison of the area of rate Vs conversion gives you an idea that which type of reactor is best suited for the given job. For low conversion, the mixed flow reactor is the best one, than the plug flow reactor. For high conversion, the plug flow reactor is deemed to be the best than the mixed flow reactor. So, the plug flow reactor will not operate with a feed of a pure reactant. In such condition, the feed must be continually primed with the product. So, an ideal opportunity for using a recycled reactor. You can see in this particular figure where we presented the graphical representation of MFR and a PFR reactor for autocatalytic reaction. Here you see that the mixed flow reactor is better. Then you can see that both mixed flow and plug flow reactor both are good, and here you, based on this conversion, you can see that the plug flow reactor is having the upper edge. So, in this particular chapter we discussed the autocatalytic reaction. We developed the performance equation for autocatalytic reaction reactors, and apart from this we discussed about various permutation and combination through which we can assess that which reactor is most optimized one for our suited purpose. Now, in case if you wish to have a further study, you can seek the help of those references which are enlisted in this particular slides. Thank you very much.